Hi, and welcome to this next video on principal component analysis. So in the previous two videos, we motivated dimensionality reduction, and we also saw principal component analysis as an algorithm for maximizing the variance when we project to a k-dimensional subspace. And so this also gave rise to an algorithm. We saw that you should pick the k largest eigenvectors of the matrix X transpose X, and this would give you the maximum variance. So we'll try to give another proof this time here. So just to remind ourselves, right, in PCA, we saw in the previous video that if we look at the matrix X transpose X, X is this data matrix having the feature vectors as rows. Now, taking this matrix and computing the eigenvectors and eigenvalues, we should choose the k eigenvectors corresponding to the k largest eigenvalues. Call those set 1 to set k, then those should be the basis of the subspace that we project onto. So we could then project the vector by computing its inner product onto each of these basis vectors and basically writing each of these coefficients in a new vector gives us a k-dimensional representation of this projection of X onto the subspace. Also something we saw before. We did not see a proof, though, that this the eigenvalues and eigenvectors of X transpose X indeed are the ones that maximize the variance. So this is what we'll try to do in this video here. We'll just go over a proof, argue why this is the right choice to maximize the variance, but in fact we will go via a slightly different route. We'll instead give another argument or now another property of PCA that we also believe is interesting in its own right. And we'll try to argue that why this choice of set 1 to set k that is given up here as these eigenvectors and eigenvalues is the right choice in some sense. Okay, so let's have a look. So we're looking for a basis, again, k orthogonal unit vectors set 1 to set k, and then we're going to project onto those vectors. That will be our projection. And the question is, again, what basis to choose? And maximizing the variance, the sample variance after projection is one choice, which is what we explored in the previous video. Another motivation is the following. So when we project, right, we can sometimes say that we're losing some information, right? So if you look at the vector X here, if we're projecting it onto P, then somehow the information that is lost is the difference between X and P, right? This X minus its projection, right? This is somehow information that we lose when we project. So why not instead say, okay, I have my data, and what I'd like to do is I'd like to minimize. I have a sample set of points, x1 up to xn. What I'd like to minimize is the sum over all of them of the square difference or distance between the original xj and the projected xj. Right, so this is kind of like a least squared loss function, like we're more used to seeing in much of the supervised learning we saw in these videos. So this is a very natural, different motivation that, try to find the set of unit vectors set 1 to set k, where you minimize this loss here, the sum of the squared distances between the original points and the projected points. So let's try to work with this definition instead of what we're looking for, and then we'll actually see that we'll end up with the same problem and the same solution. Right, so this is another way of viewing maximizing the variance. This is simply the same as minimizing the loss in the projection. So let's try to see. Okay, so we say we have our feature vectors x1 to xn, and we want to choose basis vectors, orthonormal basis vectors set 1 to set k, to minimize now the sum over all the training samples, the point xj minus its projection onto this basis. And the projection, as we already saw in previous videos, is just the sum of all the basis vectors, take the inner product between xj and zi, and multiply this with zi, and we're looking at the squared norm of this. This is what we want to minimize. Right. So of course the question is, how can we compute such set 1 to set k? And so let's start by rewriting this minimization problem. Right. So here we have a squared norm. And so let us expand this by observing that the squared norm of a vector, so everything inside here is a vector. The squared norm of a vector is its inner product with itself, right? So we just took this vector here and we're looking at its inner product with itself. This is what it is. And now let's try to have a look at all these different terms that we get here. We have these cross terms when we have this inner product here. So we get the xj multiplies onto the xj. That gives us this first term here. Then we have an xj onto this sum here, the sum from 1 to k. And by linearity, this xj inner product, the sum just moves the xj into each of the terms, right? So we're doing inner product between xj and zi. Similarly, we have the same here. We have this, the xj in the second parenthesis against the sum in the first, gives us an identical term. So we have minus twice this sum. And then we have the two sums against each other, right? The minuses cancel out, so we get a plus. The sum from 1 to k, the sum from 1 to k, summing over L, summing over I. And so what do we have, right? So we have, I guess, we get these two terms up here. Xj's inner product with Zi times Zi. And now we have to inner product this with Xj's inner product with Zl times Zl. Okay, so this is what we have here. So let's try to see what we can do with this very long expression here. So if we look at the first one here, right, we can see that this does not depend on the sets at all, right? And we're minimizing over the choice of set. So really we can just completely ignore this term because it's going to be the same for all sets. So this doesn't matter, we can get rid of it and it's the same minimization problem. Okay, the second one here, what we see is that we're computing inner product, we have some coefficients, right? These inner products that are already there, xj's inner product with Zl and xj's inner product with Zi. These are just numerical constants. And then we have Zi's inner product with Zl. And now what we require is that these Zi's, they have to be orthogonal, which means that when we're minimizing only over orthogonal Z1 to Zk, then all the cross terms where I is not equal to L, they just go away, right? Because their inner product has to be 0. So those terms go away. Okay, so that gets rid of a lot of terms. So this is what we get. We get rid of the term with the x's here. And what we have from the second part here, we only keep the cross terms where I is equal, or the terms where I is equal to L. And for those, right, we have, if we go back here, we have this term, if I is equal to L, we have this term squared, and we have Zi's inner product with itself. So it's going to look like this. And we have this middle term here with the -2 times the sum. Each of these terms is just the square. So all of this is what it simplifies to, right? So we're just minimizing this expression here. And we have some more observations we can make, right? We're also saying that the Zi's should have unit norm, which means that each of these inner products with themselves is just 1. Okay, so this term also goes away. And then we see that we have -2 times this sum of squares plus 1 times the sum of squares, as we see here. And when basically we get rid of one of them, so it's just the minus of the double sum of the squares of xj's inner product with Zi. Okay, this is what we're minimizing. Now, this is minimizing a negative number. Right? What we could do instead is we could maximize it if we negate it. So all of this whole minimization problem is the same as maximizing the sum from 1 to n, so maximizing all the sum of the training examples and the sum from 1 to k of the square of xj's inner product with Zi. And if you remember from the previous video where we looked at maximizing the variance, we saw that the variance for a single Zi, if we look at its variance, at the sample variance, if we project everything onto this Zi, we got exactly this expression here. This is exactly, we got the sum from j equals 1 to n of xj's inner product onto Zi squared. And this was when we had normalize the data such that the mean of every feature was 0. Then we got this expression here for the variance on a single direction. So it's really, as we see here, it's actually the same thing, minimizing the, so to say, sum of squared losses in the projections, like the differences between the points and the projected points. It's the same as maximizing the variance that we did in the previous video. So this is the reason why the two things are the same, even though they look different. Okay, so now we have this maximization problem, and let's try to see if we can find out what is the right choice for the Zi's, right? We already said what it is, but let's try to actually derive this, prove it that this is the right choice. Okay, so to do this, we'll just introduce a little bit of matrix notation just to simplify the expression a little bit, right? So let's recall that we typically use this X to denote the data matrix, having all the feature vectors as rows. And then we'll form a matrix set that just have these Z1 to Zk as columns. And it's the set that we're trying to pick. So what we have here in terms of X and Z, if we see what we have here, right? If we look at the product of the matrices X and Z, then, you know, if I wanted to look at the inner product between Xj, that would be the j comma ith entry in xz, right? Because that entry contains exactly the inner product between the jth row of x and the ith column of z. So we're summing, basically what we're doing is we're summing over all the entries of X set and squaring all those entries. That is what we have to maximize. So this is exactly the maximization problem. We're just summing over all entries of the product X times Z of the square of that entry. Okay. So this is the set we have to choose. We have to choose the set that has unit length orthogonal columns, where this sum over all the entries of X set squared maximized. Okay. Now, if we look at a matrix, and we're looking at the sum of the squared entries of that matrix, then in fact there's another way of writing this double sum, the sum of all the squared entries. Now, consider, for instance, I have a matrix A, right? So let's say it's an m by n matrix, and then look at A transpose A. So A is you transpose A, you multiply with itself, and let's try to look at one of the diagonal entries of this product here. If you think about it, the ith diagonal entry, right, is the inner product between the ith row of A transpose and the ith column of A. Now, the ith row of A transpose is just the ith column of A. So it's the ith column of A's inner product with itself. And just by definition, this is exactly the sum of the squared entries in the ith column of A. So the ith diagonal entry of A transpose A is the sum of the squares in the ith column of A. Now, this can be seen basically like this, right? So A transpose A, the entry I comma I of this product is you take the ith row, multiply with the ith column. The ith row here is the ith column of A. And so we just get this sum of squares in the ith column of A. Okay, so if we go back here, right? So each of these diagonal entries of a matrix A transpose A correspond to the sum of squares in a column of A. So if I now look at A transpose A and I look at its trace, right? So the trace of a matrix is defined as the sum of the diagonals. So the sum of the diagonals, if each and every one of the diagonals responds to the sum of squares in each and every one of the columns, then if I sum everything on the diagonal, I sum the squares in all the columns and hence the entire matrix, right? So just to say it briefly, if I have a matrix A and I look at trace of A transpose A, then this is just the sum of the squares of all the entries of A. Okay. So, and this is what we have here, right? Here's the sum of the squares of all the entries in XZ. So what we just said is that this whole sum is the same as the trace of taking this XZ matrix and transposing it and multiplying with XZ. And just by the rule of this transpose, right? So we reverse the order of X and Z and we put a transpose on both of them. So this is what we're after, right? We're after maximizing the trace of Z transpose X transpose XZ. And it's the set that we're choosing, right? X comes from the data. Okay, so this is just a rewriting of the same maximization problem. Okay, so let's try to have a closer look at this trace and see what we can do. So this is just what we're maximizing, right? Maximizing this trace. Now, we need something from linear algebra to proceed here. We need what's called an Eigen Decomposition. So what is an Eigen Decomposition? So if you have a real symmetric n by n matrix A, so symmetric means that the I comma jth entry is equal to the j comma ith entry, then one can write A as E times D times E transpose, where these matrices satisfy something special. The D matrix here is a diagonal matrix, meaning it has only non-zeros on the diagonal. And the ith diagonal entry is equal to the ith largest eigenvalue of A. So let's call this lambda I. Okay. Now, E here is then an orthonormal matrix, which means that all its columns have a unit length and orthogonal. The same goes for all its rows. And moreover, in this E, the special structure with E is that the ith column of E is actually the unit length eigenvector mu I corresponding to the ith largest eigenvalue lambda I. Okay, so which basically means that each of these columns here of this E are vectors that if I multiply them onto, if I take A and multiply one of these vectors, I get the vector itself scaled by this lambda I. Okay, so these are the eigenvectors placed as columns of a matrix E. And this is what you can prove, that you can write any such real symmetric matrix A as a product of E, D, and E transpose, where they have this special structure. Okay. And also, what is known is that this is real and symmetric, this matrix, then all these eigenvectors and eigenvalues are real meaning that the entries are not complex numbers, but just real numbers. Okay. So the second fact that we're going to need is that if, in addition, A is, or it's already symmetric in the first requirement here, but if it's also positive semi-definite, and we looked at this in several previous videos before, and when it becomes necessary, I'll just remind you of the definition. So if A is also positive semi-definite, then all of its eigenvalues are non-negative, right? So all these lambda i's are non-negative numbers. So this puts a lot of structure on such real symmetric matrices that are positive semi-definite. Okay, so let's try to see if we can apply some of it. So what we're going to apply this to this Eigen Decomposition, and we just saw this writing things as this E, the D, and the E transpose. We're going to apply it to the matrix X transpose X, like so the whole X transpose X. This is the one that we're going to treat as one matrix, the A matrix in the previous slide. So for this, we'll basically check that this is that it's a real matrix is obvious because it just has inner products between original real vectors. You have to check that it's symmetric and positive semi-definite. So let's have a look at it. Right. So the X matrix was an n by D matrix. So X transpose is D by N. So we have D by N times an N by D. So this gives us the D by D matrix. Okay. So it basically looks like this. And I guess entry I, j is the inner product between the original ith column and the original jth column. Okay. And what you see here is that this is also a symmetric matrix because I guess entry I, j is the inner product with the ith column and of X and the jth column of X. So if we swap I and j, we get the same, right? Then it's just the inner product with the jth column against the ith column. So it's a symmetric matrix and it's real, right? So this is easy to check. And it's also positive semi-definite. And the definition of being positive semi-definite is that for any real vector set here, it should be the case that if I take set transpose, multiply it on from the left to the matrix and multiply with set from the right, then this has to be at least 0. And this is not too hard to see because if I take this expression here, I can put parentheses around X times set and move the transpose out. And we see that this whole expression here is just X sets inner product with itself. And this is the squared norm of XZ, the sum of the square of the entries, which you can also see from expanding this inner product. And of course, such a square has sum of squares has to be greater than or equal to 0. So it satisfies all these things. It's both positive semi-definite and it's real and symmetric. Okay, so you can use both fact 1 and fact 2 with A being X transpose X, right? So what we know now is that we can take this A, the X transpose X, and then we could write it as this E, D, E transpose. D is this diagonal matrix with eigenvalues on the diagonal, and E has these columns that are unit length eigenvectors corresponding to these eigenvalues. Okay, so let's try and use this. So we take X transpose X and we replace it by E, D, E transpose. Again, E has eigenvectors as columns. The D has eigenvalues on the diagonal. They are non-negative. And we have sorted them like this, lambda 1, lambda 2, down to lambda D. And this is the positive semi-definite part that implies that these are all greater than or equal to 0. Right? All the eigenvectors have unit length and they are orthogonal. Okay. Good. So what we have to do now is we have to choose these k eigenvectors as unit length and orthogonal to maximize this trace here, right? So the sets form a matrix with these sets as columns, and we have to maximize this trace, and we're going to replace this X transpose X by ED E transpose. So this is what we do here. It now says ED E transpose in place of this. Okay, so this is what we have to maximize. Okay, so let's try and see what we can do with this. So let's now have a look. We see that we have the D in the middle. Then on both sides, we have basically on the right, we have E transpose set, and on the left, we have the transpose of that. So let's try to define A as E transpose set just to simplify things notation-wise a little bit. So then what we're maximizing, it's just the same as A transpose DA. And this A matrix here, right, it's E transpose, so E is a D by D matrix. The set matrix is a D by K matrix, so the whole product is D by K. Okay, so let's try and have a look at what this trace is. So let's examine the trace of A transpose DA. Right, so let's start by looking at D times A. Right, so A is a matrix with rows, and if we multiply it from the left with a diagonal matrix, then what happens is that this is going to scale all the rows. In particular, the ith row is going to be scaled by the ith of these eigenvalues, just by definition of matrix multiplication. So D times A is now the first row is scaled by lambda 1, the second row is scaled by lambda 2, the last row is scaled by lambda D. So this is what happens over here. Okay. Now let's try to pre-multiply this with an A, just to see what happens then. So we have with A transpose. So we have A transpose here, multiplied onto this matrix DA, where we've scaled all the rows by these eigenvalues. Okay. So let's have a look. So let's have a look. In particular, what we're interested in up here is the trace of this, right? So in the trace, that's the sum of the diagonal entries. So we need to know, what do the diagonal entries look like? So let's try to look at the ith diagonal entry, right? So the ith diagonal entry is the inner product between the ith row of A transpose and the ith column of dA. Right? The ith row of A transpose is the ith column of A, because it's the transpose. So basically what we're doing here is that we're summing from 1 to D. And then we're saying we've basically fixed the ith column of A, and we're just taking all the entries one by one, scaling them by the lambda j's, and the same entry in A again. Like, so we have the sum from 1 to D lambda j times the square of entry aj, comma I. Right. So in some sense, what we're doing here is that we're summing the entries, the squares of the entries in the jth column, but we're scaling each of them by a different value lambda j. Okay. Now the trace again was the sum of all the diagonal values. Right. So we have a sum over all I of this expression here. Okay. What we can do now is we can just change the order of summation and move the lambda j outside, as it does not depend on I, and here just rename the indices. So now we have the sum from 1 to D. So this is just changing the order of summation, the lambda I, so I changed just the names I and j, because it's usually more convenient to write entry I comma j. So we sum from 1 to D lambda I, and then we sum from 1 to j equals 1 to k aij squared. And so that is what the trace of this A transpose dA is. Okay. So what do we have now? Again, we looked at this X transpose X in the middle. We computed an eigen decomposition of a E, D, E transpose, and then we wanted to choose these unit length vectors Z1 to Zk to maximize this trace. And we defined A to be this E transpose Z. And then we saw that then we, of course, have to maximize the trace of A transpose dA. And we saw that this is the same as maximizing the sum from 1 to D of this lambda I times the sum of the squares in the ith row of A. Right, this is what we're doing here. Okay. So let's try and see how we can choose Z to do this, because now we're basically at something that's easy enough to grasp, right? So we want to just maximize this. We're given these lambda I values, and we define the matrix A that's E transpose Z. And from this matrix A, we would like this matrix A to have a large sum of squares in these rows, where we weigh the rows by the lambda I's. Okay, so I just moved everything up here, right? So we want to choose these ZI's to maximize the sum from over all the rows of the matrix A, scale the ith row by lambda I, and then sum the squares of the entries in that row. Okay. So here we're going to use a few more facts just to get a handle on this. All right, so we said that these E matrices, right, they are orthonormal, which means that all the columns here are unit length orthogonal vectors, and the same is true for the transpose of E. Okay. Now, if you ever multiply a matrix with an orthonormal matrix from the left here, then only effect that it has is that it's going to rotate the columns, which means that they're going to have the same norm and they're going to have the same inner products. You just rotate them. So you just replace them by something else. So it's a rotation matrix. It means if I multiply this E transpose onto Z here, as in the definition of A, the only thing that's happening is that the columns of A will be rotated, or of Z will be rotated. So they will have the same norm as they had before. Right? This is an important property of such an orthonormal base. It's just not change the norm of the columns of Z. Right, and we're choosing the columns of Z to have unit norm, right? These are the vectors Z1 to Zk. So which means that in this matrix A, no matter which Z I choose, in the matrix A, every column will have unit norm. Right? So I know this for a fact that no matter which set I choose, as long as I choose them as unit length vectors that are orthogonal, then the matrix A will have columns whose norms are 1, meaning that the sum of the squares in any column is 1. Okay, so this is interesting. This is the first fact that we need. Now, the second fact is, let's try and look at the row. So this says something about the columns of A. Let's try to look at the rows. So what is the row of A? Right, so if you look at it, right, we take E transpose and then we multiply it with the set matrix, right? So this is basically so if we take E transpose, right, the ith row of that one will be mu I, like so the transpose to these eigenvectors, the ith eigenvector. So these entries, right, so we're basically taking this ith eigenvector and then we're multiplying it with the set matrix, right? So which gives you a coordinate for each vector set, and that coordinate is just that inner product between mu I and set j. Okay. So now if you remember these projections again, right, so this whole row just contains all these coefficients basically for the projection of mu I onto the subspace spanned by the set j's, right? So these are just all the coefficients, and which means that the norm of this row is the length of the projection onto the subspace spanned by set 1 to set k. Okay, so every row, right, if the norm of the row is the length of the projection of mu I onto the subspace spanned by set 1 to set k, which means if I sum the squares of a row, then I get the squared norm, right? So the sum of the squares in any row is at most the squared norm of mu I, right? Because we're only getting shorter when we project onto the subspace. And this squared norm was 1, right? These were also unit length vectors. Okay. So what do we have here, right? So the two observations are, like, the first observation says that every column of A, the sum of the squares in a column is 1. And the second one says that the sum of the squares in a row is at most 1, right? Now, again, what is A, right? What was the shape of A? So A is a D by K matrix. So there are K columns, and every column sums to 1. So the sum of the squares of all the entries of A is exactly equal to K. And that has to be a fact, because there are K columns and all of them sum, or the sum of the squares in any column is exactly 1. Okay, so that's the first observation that we make. No matter what set we choose, it will be the case that the sum of the squares in the entire matrix is K. Also, the second property that we observe is that no matter what set I choose, the sum of the squares in any row is at most 1. So these two properties will hold for any choice of set. Okay. So now, okay, using these observations now, we'll try to argue what is the best choice of set 1 to set k to maximize the expression up here, sum over all the rows, weigh the row by lambda I, and sum the squares in the row. Right, so the observation here is in the thing that we're maximizing, right? If we look at this expression, everything in the ith row is scaled up by lambda I, right? And lambda 1 is the biggest value, lambda 2 is the second biggest, and lambda 3 is the third biggest, right? So intuitively, right, one can think of it like this, right? So in the matrix A, we know that the sum of the squares will always be k, and we know that the sum of the squares in any row will be at most 1. Now, so in some sense, we can think of it as a game. We're placing k values, we're placing values that sum to k inside this matrix, or where the squares sum to k. And in any row, it can sum to at most 1. And of course, right, the more we can put on the first row, the better, right? If we're maximizing, if we can put a whole mass on 1, like the sum of the squares in the first row is 1, then it's going to give us the most bang for the buck, right? Because we're going to get, this is all multiplied by lambda 1, it's the biggest value. So actually, if it's possible, right, then the best we could hope for is to have all the first k rows have sum of squares equal to 1, and then 0 in all the remainings, right? That's the best possible, right? Because any row can sum to at most 1, and we gain the most by putting value on the first row, then we gain a little bit less on the second row, or maybe a lot less, and so forth. Right, so the best we can hope for is to have the sum of the squares in the first row equal to 1, the sum of the squares in the next row equal to 1, and this being true for all the k first rows. If we can find any set that has this property, then we're happy. Then it has to be optimal. Good, so this is what we're trying to do. If it is possible to choose the sets so that the first k rows have the sum of squares equal to 1, then it has to be an optimal choice of set. And now here is actually a concrete choice that achieves this. So let's have a look. So what I do is I take the ith of these sets that I'm choosing, and then I just let it equal mu I. Right? Because then what's the case? Like, look at A. What are the entries of A then? Like, let's look at entry I, j. Right. So entry I, j is the inner product. Basically take the ith row of E transpose. That row is mu I by definition of E. And then I have to multiply this with the jth column of set. Well, this is what I just defined to be mu j. So entry I, j of A is then mu I's inner product with mu j. Okay, so what is this, right? So we already know that, well, if I is equal to j, then it's going to be 1 because all these vectors have norm 1 as it says over here. If I is not equal to j, it's going to be 0. So which means that for this choice of the sets, my A is going to look like this. In the first k rows, I'm going to see a 1 on the diagonal, and then everything below is going to be 0. And as we just argued, right, this actually puts a whole sum of squares of 1 in the first row, a sum of squares of 1 in the second row, all the way down to the sum of squares being 1 in the kth row. So you cannot possibly make a better choice, because this is going to maximize the sum of when we weigh them by the lambda rise. Right, so this actually proves that the best choice of set 1 to set k are these mu I vectors, the k eigenvectors corresponding to the k largest eigenvalues of x transpose x. This is the optimal choice of set 1 to set k. Now we actually proved it. And this is what principal component analysis of PCA does. It chooses these vectors set 1 to set k. And then we want to project onto this. We could just compute the projection as the sum over all these set i's, inner product between x and zi, and scale it by zi. And if we wanted to, and we could also just write it in this basis, then we would just have a k-dimensional vector. The representation of this point will just contain all these inner product. And this choice of set 1 to set k actually minimizes the squared loss of these projections. And as we also argued, it actually also maximizes this variance that we mentioned in the previous video. Right. And we can always write x in this new basis. Right. Okay, so this completes a proof, or at least an explanation for why you would actually make this choice of set 1 to set k for principal component analysis. In the last video on principal component analysis, we'll look at some useful things to keep in mind if you're using this in practice. Good, so let us end here.